on YouTube now. And we should be going live we are live now. So over to you, Jeremy.
Awesome. All right, let me just share my screen real quick. Let's see. Actually, yep, right here. Okay. So yeah, thanks everyone for joining this meetup today. I'm going to talk about some things that I've learned building threat detection systems as a machine learning engineer. So I've been working at the intersection of machine learning and cybersecurity for the past 5 or so years. I spent 3 years at Proofpoint, which is largely an email security provider, and there I was building models for phishing and malware detection. And I now work at Duo, where we're more focused on providing security for authentications. So this talk is largely going to be like, I'll talk through the process of building a threat detection system. And then I'm also going to attempt to kind of like relate that back to the general process, since I know we have a wide variety of ML practitioners here today. So I'll kind of like relate that back to just like building machine learning systems in general and try to highlight like some of the unique aspects of applying machine learning in the cybersecurity domain. And just wanted to give like a quick shout out to all of the wonderful people that I've worked with at Proofpoint and Duo that have helped teach me about the field and influence my thinking on the intersection of cybersecurity and machine learning. So yeah, just a quick disclaimer: like the views and opinions that I talk about are of my own, don't necessarily reflect my current or previous employers. Okay, so like just as some context to start off, like cybersecurity products in a nutshell, like I kind of view like in an oversimplified manner, like there's like two main pieces. Like we want to implement secure protocols, but some of these, like there could be weaknesses or vulnerabilities in that. So there's also this need to be able to detect and block threats. And that second piece is really going to be today's focus. We'll talk about building threat detection systems. Okay, so how do you do that? How do you build a threat detection system? Again, kind of like at a high level, there's 3 big requirements that we have when building a threat detection system. We want to make sure that it doesn't interfere with benign content, it identifies and blocks threats from causing harm to users, and it doesn't impose an undue burden on the users of your product. So kind of like talk through the general process of the different pieces that go into building these threat detection systems. And to start off, you really have to understand the threats that you're trying to detect. So for your given, like, if you're working at a cybersecurity company, you kind of need to understand like, okay, what is our security product that we're offering? What's the potential attack surface of that product? What are attacks that threat actors are leveraging in today's landscape, and really like be able to have those discussions about threats that are relevant to our product. And it's important to be able to like use a shared language and taxonomy when talking about these threats, so that when I'm talking about a certain type of threat, like you understand what I'm talking about. Like we're using the same language, and the like information security, like in threat research communities, are pretty similar to the like machine learning communities in that they're like largely very open communities and like to publish research and like be involved at a community level. So there's like also a lot of value in being able to like be a part of that like larger community that's discussing active threats that various organizations are discovering, and sharing exploits so that we can all build better protections and defenses and be able to effectively stop these threats. And so far, like I think this is very much like run-of-the-mill like machine learning process. So like in any domain that you're applying machine learning, it's important to like build that understanding of the problem, like build some background in that domain, understand the language of that domain, and be able to like very precisely define like what task you're trying to automate. So, for example, in the world of threat detection, we need to be able to like very specifically state like, these are the threats that I want my system to be able to detect. So far, this is like, I think like a part of the process that all machine learning practitioners are familiar with. And it's, equally important in the cybersecurity domain as well. And once you have that kind of like understanding of the threats and you've specified, the problem and like what threats that you're trying to detect for your product, the kind of like a natural place to start is with rules. Like, at this point, we don't have like big labeled data sets we can train models on. So we're really forced to like rely on our domain knowledge of those threats and encode that in a set of detection rules. And like I mentioned earlier, we want to make sure that we're like not interfering with domain content. Ideally, like a good threat detection system, you're able to take action on those detected threats and block them from causing harm to users. But we want to make sure that we're not blocking, benign content, because that gets in the way of our users. So these detection rules need to have very high precision. So we kind of like, when we're defining these rules, we need to focus on like threat fingerprints to be able to like, define that rule such that it's not going to flag benign content. And then, when we're starting out building this threat detection system, we have to build a lot of data infrastructure required to like process all of those events and apply these heuristics to those events to be able to block the threats and let the benign content through. And that same infrastructure, we can then leverage at a later point with our machine learning models. So I kind of like related this back to the general machine learning process. Like still at this point, I think this is like very common across domains. It's like, pretty common advice that you'll hear to, start with a heuristic and deploy that into production and get some of the value of that like kind of like automated detection and use that to kind of like collect your data. And then you can take that data and like, label it and build training data sets to then replace that rule with a machine learning model at a later point. But like usually you start with a rule. And same case here for building threat detection systems. So yeah, I mentioned like, okay, you start with rules, deploy it, and start collecting data. Really the next step in building a threat detection system is starting to annotate that data, which again is like very much in line with the traditional ML process. And even if we're not really looking or like entertaining machine learning models at this point, those labels are still really valuable for being able to quantitatively evaluate the rules that we're developing. So we want to make sure that I mentioned like those rules need to be high precision. We want to be able to start to quantify that before we're like deploying them out to production, so that we're confident that they're not going to flag a bunch of false positives and block like benign content. We also want to make sure that those rules can actually catch threats and are detecting malicious content. So those like labels that we apply to our data is really useful, like during rule development as well. And it's important here, I think, to make sure that we're labeling our data according to that threat taxonomy that we defined at the very start, where I was saying like understand the threats that are relevant to your product and like build out a taxonomy, because these labels are contextual and dependent on the threats that we're trying to detect. So if we take for an example, like say you have this third-party design firm that's partnering with an e-commerce company to like redesign their website, and say they deploy a non-functional version of this redesigned website on the design firm's some random subdomain on that design firm's website, to use that to kind of like demo their work and get feedback with that e-commerce company that they're partnering with. If we're looking at that web page and trying to make a judgment from the perspective of like labeling if that's like a phishing URL or not, then no, not necessarily. Like if it's like a non-functional website. Like, it's not gonna try to steal anyone's credentials or anything. So from a phishing perspective, like, that's perfectly benign content. But say we also had like kind of like a brand protection model where, like, companies want to know like where their brand is being presented online, or like, identify like potential impersonation attempts. And for that model, like, maybe that website is a true case of that, where we would want to label that as like a brand impersonation, even though like in that case maybe it's valid partnership, but we'd still like want to be able to train the model to identify those types of cases. So those labels are contextual and dependent on the threats that we're trying to detect. So that's why I think it's important to be able to label your data to that taxonomy. It's also important to be able to collect the necessary information to apply labels to your data. And this is, I think, like one of the really challenging areas of applying machine learning and labeling data within cybersecurity. So a couple of examples. If you look at this URL and are trying to label it as like, is this a phish or not? Just looking at the URL alone, it's kind of hard to say. Maybe it's a phish. Like, it looks a bit unfamiliar to me, but I don't know for sure. And I grabbed this URL as an example from a website called PhishTank, which is kind of like an open source feed where people can submit URLs, and then the community kind of like makes a judgment of whether it's a phish or not. And in this case, like, this is not a phish. But it's like, just looking at the URL itself, it's kind of hard to make that judgment. We might want to look at things like, what was the DNS registration for this? You might want to like look at like, okay, what is this interbank.pe? What does that website look like, and how does that compare to this like web page that we have linked here? And maybe you want to like be able to interact with that web page and like try to figure out if this is a phish or not. So there's like extra context that's required to be able to make that judgment of like annotating if this is a phish or not. Similarly, if you're looking at an authentication log, like, this user is trying to access this application using a given device. Just looking at this login in of itself, it's really hard to say if that was like a legitimate login attempt or not. There is additional context that we need to be able to take into account when making a decision of like, is this actually me trying to log into something, or is there, is there some compromised account that like a threat actor is trying to access? We like need additional context. And again, I think this is like, also pretty like standard. I mean, in some cases, like say you're like labeling images, like you might have sufficient context in the like data itself to be able to, look at that image and say like, oh yeah, there's a dog in that image or not. But if you're like labeling, if you're like images for like a radiology domain, like maybe you need that domain expert to really be able to like go in and help you label that. So there's like context required and domain expertise that's required when annotating your data. Definitely like still the case in building threat detection models. Okay, so once we've got like we've deployed our rules and we've started to annotate our data, and that's like a continual process, but we've started on that and started to collect some labeled data. Oh, sorry, one more slide here. I just wanted to, I really like this slide, or this like image from Matt Kelsey, just like, trying to visualize the the complexities of different labeling workflows for machine learning systems. And I think labeling is a arduous process. We try to do it in a like efficient manner, but it's like it's definitely a hard part of the overall process. And this is like not relevant or not relative to cybersecurity, but just like training, like labeling data for training machine learning models in general. So yeah, just like relating that back to the overall ML process, like labeling your data is a hard part of the job. But once we have those labels, we're really able to like start to scale our detections and introduce machine learning into our threat detection stack. And the way I think about it is like, because we have to operate at this really high precision constraint, because we don't want to like flag benign content and start like, blocking users from being able to do their work. We have to operate at this like really high precision. So introducing machine learning helps us like push out our recall on being able to identify and block those threats. And one of the areas where like this starts to look different than applying machine learning in a lot of domains is, instead of having a machine learning model that just replaces the heuristic, these two systems work together. So we keep our existing rules, but we're complementing that with ML-based detections as well. And when you're rolling out machine learning as part of a threat detection stack, you don't necessarily need to like immediately turn on that, like build machine learning models that you can turn on and block content. And like machine learning also serves a really useful purpose in this like threat hunting exercise of just being able to like look at the large amount of data that we process and try to identify threats in that data. And I've built some like kind of like internal tools that are really more targeted to like empowering threat researchers to look across all of our data and find examples of threats. So like you can imagine here, like a search engine basically on all the data that we're seeing, and kind of like giving threat researchers that are writing rules for detections like superpowers to be able to find malicious content that we don't currently have rule coverage for, and finding that content and adding rule coverage for. But yeah, like I think this is a really interesting area because, as I mentioned, like we're not necessarily replacing the rules with machine learning, but the two are working together, and they each have their own like unique strengths. Like for example, say a customer comes to us and says like, "Hey, you blocked this URL or authentication attempt, and that was actually me logging in," or like that was like a perfectly good URL. But you blocked it, and like they might be upset that benign content was blocked, and it's a lot easier to remediate those situations with a rule and just update your rule to make sure that content isn't blocked, like that specific content, than it is to like update a machine learning model and like take that example and include that in a training data set and like retrain your model and redeploy the model. You can remediate false positives a lot more quickly with rules. So like the rule-based systems still have their value as part of the threat detection stack. And the two really work together. And because the two work together, it's actually really interesting to look at when those systems disagree. So what are the pieces of content that our trained models classified as malicious, but the rules thought it was fine, or vice versa, like rules flagged something as malicious, but the model didn't. And in both of those cases, like, if the rule caught something that the model didn't, maybe we can take a look at that and label it appropriately and include that in the training set so we can improve the model. And then similarly for, if the model caught something that the rule didn't, well, maybe we can take a look at that, and if it's actually malicious, we can try to evaluate could we realistically write a rule to detect that and improve our rule-based detections of that. And in some cases, the logic might be complex enough that the answer is no, just let the ML model catch that. That's what ML models are great at. But in other cases, you might be able to write a good heuristic. And then we can kind of have defense in depth of having these multiple systems that are detecting and flagging content. It's kind of like the Swiss cheese theory of security, where you have multiple layers of your system, and each layer has some weaknesses and some holes, but when you stack them together, you get a solid defense. Another like really interesting thing that I've learned working in this field is like building detection systems. We often operate on a large volume of events, and there's a need to do detection in an economic, like an economical fashion. Like we can't just like throw the biggest, fanciest model at all of the data. We have to be like, a little more cost effective with our detections. And so what ends up happening is you have these like cascading systems where you have, at the start of the pipeline where you have like all of the events that you're processing, you have these like cheap, fast inference like models and heuristics that, rely on, features that are easily accessible and can quickly run. And they can make judgments, and maybe they can make judgments on like 60% of the data, and then for the other 40%, you can pass that along to more expensive models. So it's kind of like the just enough and no more principle when making a decision of whether something is benign or malicious. So like there's always this need to balance the efficacy of our threat detection systems with the cost, and the cost could be like the resources associated with running that model. Like, do you need GPUs to run the model or not? It could be the resources associated with going out and gathering the data that your model needs. Like, it's a lot more expensive if you're looking at URLs, for example. If you just need the URL itself, that's a really cheap feature. But if you need to like send a web crawler out to that URL and like capture features of that active web page, like that's more expensive. So there's costs associated with that data collection. And then there's also costs associated with just like the inference time. So a lot of times we're sitting between like, events and users and trying to make a judgment of, is this like content safe to pass on to the user or not? And we need to do that quickly. Like if I'm like logging into an application, I don't want to hit the submit button to log in and like sit around and wait for a minute for that system to like try to figure out if my credentials were compromised and I was like, a bad actor, or if I'm like, the actual user trying to log in. We like users expect these decisions to be like, lightweight and not get in the way of their work. So like that's part of the cost equation too, is we need to be able to make fast decisions. Okay, so the like next big lesson that I've learned in building threat detection systems is like it's really important to focus on the threats and not necessarily just like the anomalies in the data, because there's so much weird but perfectly benign content on the internet that if you're building like an anomaly detection model, there might be a misalignment between things that your models surface and like the value that our customers are expecting. Like at the end of the day, we're a security product. So if you're working at a cybersecurity company and building a threat detection system, like that's a security product. So we need to like make sure that those models are providing security and not just like showing like weird content. So evaluating content from the perspective of those threats that we're attempting to detect and block. That's to say, like, not to say that anomaly detection doesn't have its place. I think it can be a really valuable perspective as well for like threat hunting, of like, being able to have some feed that shows you an anomalous content that, maybe some subset of that is actually threats that we care about, that might have evaded our detection systems. But we just like have to be careful to like understand that weird does not imply malicious. And so one example of that is, say, this website, where if you look at it, it's like, oh, there's the Fidelity logo and like a login field. But if you look at the URL, like that's not Fidelity's URL. Like that's strange. So is this web page weird? If you're like building a phishing detection model, yeah, this is a weird edge case. But is it a threat? no, it's just like a web archive. And like, this is a reputable archive website that, this page isn't, this page isn't going to like, try to steal your credentials. So yeah, there's so many examples of this, where there's like just weird content online that isn't inherently malicious. But if you're like just building anomaly detection models, you're going to find a lot of stuff like this. So an interesting thing to keep in mind is like people are building threat detection systems. The next lesson is a really fun one that I really enjoy thinking about, and it's how we can mitigate detection errors with designed solutions. So I mentioned before, when we're building threat detection systems, we want to be able to block the threats, but those like blocking parts of the system need to have extremely high precision, so we're not blocking benign content and frustrating users. But that prevents us from like being able to effectively mitigate all of the threats out there, because we need to tune our model thresholds and rules to make sure that they're not firing on benign content. So how can we like go a step further and protect our users from some of those threats that fall in that gray area? And that's where I think it's, there's a lot of value in being able to shift your perspective from this binary outcome of like, do I allow this content or do I block it, to this gradient of possible outcomes. And this is a design problem. How do we treat that content that falls into the gray area between benign and malicious, of content that looks like it could be malicious, but we're not exactly like confident enough to make a blocking condemnation. And what are ways that we can provide our users with additional security in these cases? So a couple of cool examples that I've seen in my experiences. One example from Proofpoint of looking at their like isolation browser. So here we're looking at like URLs and evaluating if a URL is malicious or benign. But say there's a URL that like we're not entirely sure, like we can't conclusively say that it's malicious. But we also know that this person gets attacked a lot. So we might like have them open that URL in this case, like this isolation browser, where it's like a little bit of a more locked down environment, and can prevent the user from accidentally leaking information that they might not want to. So yeah, in cases where we can't like outright block content, we can redirect some of those users to more secure environments based on additional context. And looking at Duo, we have risk-based authentication. And here we're making like intentional choices about when we increase friction in the authentication experience, to try to like separate the user experience between benign and malicious users. So if there's a login attempt that looks strange and looks like it could potentially be a threat, but we're not confident enough to just like block that login attempt outright, then we can require the user to use like a more secure second factor when they're logging in, so that we have some like additional assurances that the user, like the person logging in, is actually the user that they say they are, and not a threat actor that had compromised primary credentials that's trying to log into their account. So this is like a really interesting area of like, when we build machine learning products, there's probabilistic output, and like how do you design around that? It's a really interesting area that I enjoy thinking about, and it's fun to think through like how we design security products to account for that. And then the last big thing is like I've learned it's important to understand that we're playing an infinite game when it comes to threat detection. So it's a really cool environment to develop machine learning and to deploy it, because it's a naturally adversarial environment. So say we discover a new threat and we build detection capabilities to block it, threat actors, and so we start blocking this threat. Threat actors are usually pretty sophisticated. I mean, it depends on, there's a variety of different threat actors, but The sophisticated ones will actually track their efficacy of like different campaigns where they're trying to like they're delivering a threat and trying to profit from that. And they have metrics. Well, they'll track like how effective those campaigns are. So if they notice that their campaigns are less effective now, that's gonna, and they're gonna profit less from those threats and exploits. They're going to be incentivized to go find a new vulnerability to exploit. So they're like continually incentivized. As we improve our defenses, they're incentivized to find new vulnerabilities. So it forces us to really stay nimble and be able to adapt to those new threats in this like continuously evolving landscape. I thought this tweet was funny of like saying like we can't just look at like build some really fancy machine learning model and like that detects all the current malware and says like, okay, we've solved the problem. Like we can go on and do different things now because like security has been solved. Because that model might be great at identifying the malware that exists today, but this is an infinite game. These threat actors are going to be incentivized if like we're more effective at blocking their current exploits. They'll be incentivized to go find new vulnerabilities that they can exploit. So it's like a continual kind of cat and mouse game. And like as a result of that, like just again emphasize like cybercrime is big business and like there's a lot of money to be made by these threat actors by exploiting vulnerabilities and compromising users. So we have to always be able to improve our detections against those threats and be nimble to be able to identify these new attack vectors that pop up and build defenses for that as well. So yeah, that's like, just a little bit of what I've learned building threat detection systems and like trying to look at how machine learning fits into that picture. And all of the thinking that goes into building threat detection systems. So yeah, thanks for listening and spending the time. Go enable two-factor authentication if you haven't already. I hear Duo has a pretty good product. And yeah, any questions?
First, plus one on that, Duo has a fantastic product. I use Duo for almost all my 2FA. I learned about it from Georgia Tech, and it's one of the only few 2FAs that actually have send a push, and then I can just approve it. So I really like that product.
Awesome. So plus one for Duo. Glad to hear.
Jeremy, that was a fantastic presentation. I really loved how it was so practical and tried to marry the product design decisions, especially your lessons on mitigate error detections with design, right? Like how do you tackle that middle ground and cascading systems and attention. So we have a lot of questions in there. I'm gonna just go through based on popularity when people thumbs up, thumbs down. So again, reminding everyone to just please look at the questions if you can, and just indicate which one you think is important. So the first question, how do you handle situations when your machine learning models conflict with the rules? So you spoke about this a little bit, right? Pay attention when the rules disagree. Do you update the rules? Do the rules override the decision? How do you address that tension between your rules and your models?
Yeah, so it's like a really interesting area because we're deploying machine learning models alongside rules. And so like it kind of depends on the scenario. So say we have some content that our models are catching and our rules aren't, or like a model is flagging something as malicious, but the rules aren't. There's two possibilities. The model could be wrong or the rules could be wrong. If the model is wrong, then like that's good to know and we can incorporate that into our training sets. If the rules are wrong, then we can look at like our existing set of rules and try to figure out like, could we define a new rule to like, accurately encapsulate and like start detecting this threat in the rule-based system as well. Even though like at the end of the day, we're still blocking that content because the model caught it, we want that kind of defense in depth of having multiple systems being able to flag that malicious content. And then it's the same for when rules are flagging content that the model's missing. Like maybe that's a bad rule and we need to update the rule. But maybe the rules are catching some piece of content that like our models really should as well. And again, we would like, take and push that to a labeling queue and annotate that data and build it into a training data set, like, retrain our models. And that's something that like in cybersecurity, the data and like landscape is moving so fast. Like you need to be able to like kind of like continually be adding to your labeled examples and retraining models to be able to keep up with this like shifting data domain.
Fantastic, thank you. The next question: have you considered semi or active learning approaches to get more labels? Any advice or lessons there? So I saw that you mentioned that as well in one of your lessons, I think 5 or 4.
Yeah. So it's really interesting because a lot of these threat detection problems are working with really highly imbalanced data sets. There's a huge amount of benign content, and there's a lot of threats too, but like they can kind of be needle in the haystack in some cases. So just looking at like a random sampling of content on the web, if you're like labeling a phishing classifier, for example, like by and large, you're just going to be labeling a bunch of benign content. So active learning is like a critical component of that. And there's like, and what I've seen, you have these different sampling strategies for active learning. So those discrepancy feeds that I mentioned, where like the rules and models are disagreeing is one potential like feed of information that might populate your labeling queue. You might have like surrogate models that are like, trained just to like highlight content that you should investigate and label. You might look at like things close to a decision boundary and initially train a model and run that on a whole lot of production data, and then sample based on like what examples lie close to that decision boundary to figure out like additional content to label. There's like, in my experience, you like define like 6 different sampling strategies, and then the labeling queues are populated as like this mix of different sampling strategies. But those are like critical, and sometimes you still do have like a random sample that feeds in, which can be useful for like approximating like the training data sets that we build. Usually those are like balanced data sets where we have like equal amounts of malicious and benign content. And we'll like capture and determine metrics like precision and recall based on the labeled instances that we have. But then we have to try to like back calculate like, okay, if we were to deploy this in production, like what would the true precision be, understanding that like the 2 classes are going to have a different distribution. And so sometimes like the random sample is useful to bring in some of that to our labeling queues as well. But yeah, it's active learning is, I think, like a critical component. The other thing I'll say there is like, as far as like semi-supervised learning, another area for like trying to efficiently label data is sometimes like bulk labeling, which like you can kind of view semi-supervised learning in that, where like, we're trying to like, propagate labels to more examples, or but I've like I think because the labeling process is so difficult, we try to be as efficient as possible and figure out like, okay, it's like really laborious to just like sit and look at like examples one by one. So what are ways that we can kind of like look at groups of observations and be able to make a judgment and kind of like in bulk labels?
That's fantastic. I took down a lot of notes because that's something I think about a lot as well. So surrogate models, close to the decision boundary, all of this. And of course, if you have multiple strategies similar to what we have, we pick those that that have the highest discrepancy. Fantastic. Are you concerned about adversarial attacks on ML? Evasion, like people might try to learn about your model and try to evade around it.
Yeah, definitely. And it has interesting applications. So like, yes, this domain is an adversarial environment. And so like one interesting implication is, for example, like when we shift from that like perspective of having like allow versus block to like having a gradient of possible outcomes, like to a threat actor, that's giving them more signal about our decision. So like if you look at like model stealing or like like people that are trying to figure out how to break a model, the more the more information you give them about like the model score, the easier it is for them to break, or like steal the model weights, for example. So yeah, it's like an important consideration too of like, it would be a really bad product if you're like, if your detection engine was just like exposing like our like raw prediction score of like, I think it's like, if we have a detection model that's like, outputting scores from 0 to 1, and we're just like including that and like sending that off to what the user sees, that like, threat actors could look into like that. Like we definitely don't want to do that. And we want to kind of like be a little guarded about how we're like using the outputs. Then there's also like, just like adversarial attacks. Like, so I've worked with some like vision-based models classifying phishing pages, and they're like, within the computer vision community, you have people that are like trying to put patches of like, basically like figure out patches of noise that they can include in the image to confuse models. I haven't seen a lot of that in practice on websites. I think some of those like patches just like look strange, but it's definitely a conversation that comes up.
Nice. Next question: do companies typically have the same model for all threat types, or a model for each threat type? I guess maybe the question is, your models, are they multi-class or one versus all?
Yeah, I think you can have both. I think you have different types of models. Like, so if we're looking at from the perspective of like the cascading systems, and where we're trying to like, balance the efficacy and cost and like the amount of like the data volume that we're processing on, you end up with different kinds of models for depending on like what information you have available. So yeah, like I think like you don't just like take the same model and train that for like all of the detection tasks, because in some cases we need to have like really cheap and fast inference. In other cases we want to have like, we can tolerate more cost with like data collection and model latencies. So we want a different architecture that can be more efficacious.
Gotcha. Chip, you had a question?
Yeah, just because Jeremy mentioned latency, so I wonder, like, I want these models online and they have to respond very fast.
So I only caught the first part of that. So let me know if I didn't address it fully, but when we have like threat detection systems that are blocking content, like at least like the inference needs to be online. There's also security products that like focus more on alerting. So for example, at Duo, our first like machine learning product that we released, it's called Duo Trust Monitor. And that's more like an alerting focused model that it'll look at like, a company's authentications and like user behavior patterns, and we'll surface things on a schedule to security administrators to like go in and investigate. And in that case, we're not like making a decision during that authentication. And we're just like, taking a look and surfacing those events. So in those types of cases, like where we're just alerting, like it might be a batch system and you can tolerate more latencies, but definitely when we're like making a decision like whether to like block content or not, or even just like for risk-based authentication, like that's happening during an authentication. So we want that to be like a very fast decision, so that you can have like a quick login experience and you're not just like waiting for us to try to evaluate your login and figure out like what second factor we will like require from you.
So it's like in the order of seconds, not like millisecond.
For like
for the blocking authentication. Yeah.
Yeah, definitely less than seconds.
Yeah,
like that.
think
Those
so.
types of decisions need to be in milliseconds.
I would think so. If not, a lot of users would just stop using the authenticator.
Right. Yeah.
So can I ask a follow-up question, or should we continue with the Slido?
Yeah, I
Great.
got another question in the Slido. So how often do your threat patterns shift? How often, I guess, do new threats emerge often? How often are your, and of course, how often are your models retrained? But I guess if your models are retrained, but you don't have new labels about this new threat patterns, it really doesn't help much.
Yeah, it's a constantly evolving landscape. I think as far as like model retraining schedules go, it kind of depends. Like, say if you're training like a phishing detection model, like that might be like you might be able to get away with retraining your model like every couple of weeks, like every month or so. And yeah, like you need to be labeling data in that interim. So like when you're retraining models, there's like fresh, like more recent data to be able to train on. For other models, like so for that like alerting based system that I mentioned through a trust monitor, that's more of like looking at like user behavior patterns. And we can train those models in like more of a self-supervised fashion. So we actually like currently train that on a daily schedule. So that's like always like very recent. And we've talked about, revisiting that and like maybe pushing that to a weekly schedule. But yeah, I think there's like, those different considerations of like, costs associated with training versus wanting to be like, using the most recent data. And there's a trade-off there.
For sure, I really I understand well the trade-off in terms of cost for retraining some of the bigger models. So we have an interesting question that's top of the vote, but I want to leave that for the last one. It's a slightly different non-technical question. I guess the second question is, with regard to labels, what helped the most? If you could share augmentation techniques, hard mining, or is it just active learning and supervised, semi-supervised?
Yeah, so I think we spent a lot of time looking at like different ways to make the labeling process like most efficient. And it's usually like, I think a good setup is you have a system where you can define like these different active labeling sampling strategies, and like hard negative mining can be one example of a sampling strategy. And you kind of like are able to pull from these different sampling strategies to figure out like what to bring into your labels. And in the past, I've like with various labeling infrastructure, like sometimes you can choose like for a given labeling queue, you can choose to say like, I want to label instances that were used with this strategy, and kind of like figure out like what data you want to pull from the various sampling strategies, and kind of like get a feel for each labeling strategy and whether that's showing you interesting, useful data to improve the models. The other like area is like if you identify the models like missing something, that like, I mean, I guess this is kind of like hard negative mining in a sense. Like if the model is not performing well, and like, say we're like a visual based model that's looking at web pages, and it doesn't perform well on pages like sparse pages where there's a lot of like white background and very little content. Like you might observe that in your error analysis and then go like specify a query to like collect more examples of that so we can train and improve the model. So it's definitely like, Andrew Ng has this big push for like data-centric machine learning. And I think there's a lot of value in that when building threat detection models as well.
Thank you. I really like the very practical mix and match, have everything and let I don't know, your product managers or your data scientists just choose. Last question, it slightly deviates a bit. Where do I start from if I want to pivot in this field? I'm currently a cybersecurity engineer, but want to add a flavor of machine learning.
Yeah, that's a really interesting question. So I think if somebody like has cybersecurity experience, like the easiest place to start is like building out those like rule-based systems, and like getting experience, like kind of building those detections, and starting to like include some parts of the machine learning process, like make sure to like start to like put together labeled data sets so you can evaluate those rules. And then in tandem with that, like start to, take like ML MOOCs or like classes, or like get a basic understanding of the machine learning process and understand some of the more like, classified or like classification models that you can apply to that labeled data set. And then just kind of like, when you're training those models, like compare that to your rule-based system. And I think, somebody that is coming in with domain expertise on cybersecurity, like they have a lot of like really valuable experience in like informing like what are the sets of features that we want to include in training that model. So I would say to that person, like, you're already halfway there. Just like spend some time to like study up on the machine learning side. There's tons of great courses online to like, build your basics in machine learning, and then like try to like do that alongside the like rule-based systems that you might be working on, and kind of like build like what's the word? You can say like like marry the two systems together and like be able to look at like how they interact.
Awesome. So I would also now like to open the floor to questions. So anyone in the Zoom chat, feel free to post your questions in the chat, or if you want, you can just unmute yourself and speak. I guess everyone was very diligent about posting their questions in the Slido. Anyway, I wanted to just thank, Chip. Chip has questions.
Oh, you're muted.
Chip, I think you're muted.
Should we stop recording or?
Yeah, I think this is a good time to stop the recording. Thank you everyone who's been listening on the live stream.